unmute myself here. Okay, good. So last time we were talking about we're kind of doing like a quick overview of all of the quantum stuff that you probably did in Physics 200. And we're going to continue with that today. So let's just recap what we've talked about so far. We introduced this Schrodinger equation. It's a differential equation in time and position. And when you solve it, you get solutions for this wave function. That wave function, when you square it, it's going to give you the probability distribution for finding a particle at a particular position and at a particular time. So this position and time dependence are both governed by this Schrodinger equation. So it's like our axiom of quantum mechanics. It leads to these solutions that we want. Once we have the wave function, we can calculate things from it. So for example, the probability of finding a particle between x and x plus dx is given by the absolute square of the wave function times the width of your interval. If we're going to treat the square of the wave function as a probability density, then it has to be normalized so that if we integrate over all space, the probability of finding our particle between plus minus infinity should be equal to 1. And so that's called normalization. If we were to plot the probability density or the square of the wave function at a particular time, it might look something like this. And so this is telling us here at the peak, this is where we're most likely to find our particle. But just because we do a measurement doesn't mean we're guaranteed to get it there. We could get it anywhere, and the height of this line is telling us the relative probability of finding it at a particular position. So another one of these ideas was that before we make a measurement, all we can do is really calculate this probability distribution. But as soon as we do make a measurement, then we know exactly where the particle is, and that dramatically changes the wave function instantly. And so this is called like the collapse of the wave function. So immediately after the measurement, if we found the particle at this position, let's say it's at 0, then all of the probability is very focused around that point x0. If you wait a long time after the measurement, this will again start to evolve and spread out, governed by the time-dependent Schrodinger equation. So this is, I should say, this is immediately after a measurement. Okay, so what I want to do today is I want to show you some examples where we can see some of these effects. Again, this is probably something you talked about in Physics 200, but it's a good reminder. Okay, so we can see the effects of wave function collapse and this so-called, remember we thought about like this way of thinking where we had an ensemble of a huge number of replica systems prepared in exactly the same way, and then we imagine we let the system evolve a certain amount of time, and then we go and measure all these replica systems one after another, and we come up with this like ensemble of outcomes where, you know, when we make measurements of a position, we're going to get a different x for each one of them. But if we plotted a histogram of those, then we could recover the original probability distribution. So I'm going to call that the ensemble average picture. By looking at the two-slit experiment using electrons. So you're familiar with the two-slit experiment using, say, a laser pointer or something like that. You have two narrow slits cut out of a slide. You illuminate those slits with a laser pointer and you project the image onto a screen. And what you see is some kind of interference pattern where there's bright spots and dark spots. This is easy to interpret in terms of classical physics if we think of light as a wave. When the light passes through the two slits, a ray from slit 1 and a slit 2 arrive at some point on the screen, but because they come from different slits, their path lengths are different to get to that point on the screen. If the path lengths differ by some integer multiple of wavelengths, you get constructive interference and a bright spot. However, if the path length difference comes out such that you're at a peak and a minimum of one ray is at its peak in its oscillation and the other one's at a minimum, they destructively interfere and you get a dark spot. Okay, so that's the idea. And so now we imagine doing that with electrons. And so we have the same thing. We have two slits, but now we're not going to illuminate them with light. We're going to illuminate them with a bunch of electrons. And we're going to project those electrons onto a screen. This is like a side view of a flat screen. So this is a side view. And then if you take that screen, rotate it 90 degrees so that you can see what it looks like, you get this interference pattern. And so here's the picture in terms of quantum mechanics. This interference pattern only makes sense if we give the particles some kind of wave character. And so that's like the de Broglie wavelength, so matter waves. And then after that, everything's the same as with what we saw with light, except for some important details. Okay, so the electron, if it's a wave, it goes through the two slits simultaneously, and different parts of the wave travel different lengths to some point on the screen, and you can get constructive or destructive interference. What's different about the experiment with electrons and with light is the following. I could decide that I'm going to send these electrons in very slowly, one at a time. So not as it's drawn there, where we have, tens or hundreds or thousands or millions of electrons all at once. Imagine sending them one at a time. Then it goes through the slit, and we don't know where it's going to hit. All we can do is calculate some probability of where we're likely to find it. When it arrives at the screen, it leaves a little indication of where it hit. That's like our measurement. So when it hits the screen, we know where it lands, the wave function collapses, and we see exactly where that hits. So if you do the real experiment with electrons coming in one by one, this is what the time evolution of the screen will look like. At early times, when we've only passed through 7 or 8 electrons, it looks like we're hitting the screen at random spots. It still looks pretty random after we have 100 or so electrons. But then once we have a large number of electrons, like maybe this one, if you know to look for stripes, a stripy interference pattern, you can start to see it. But if you didn't know what you were looking for, even in C, you might say that looks more or less random. But then in the limit of a huge number of electrons, the interference pattern, the bright spots with dark spots in between, starts to emerge. Okay, and so I want to say a few things about this experiment. So electrons with the same energy and momentum are incident on a double slit. Interference is observed even if electrons are incident one at a time. And so the interference pattern that is observed, interference pattern is only possible if the electron has wave properties. Okay, so that's the sort of broad understanding of the experiment. So after an electron has passed through the slits, whoops. So pass through the slits, but before hitting the screen, all we can do is give a probability distribution for where the electron will hit. Okay, so once an electron is detected, and our detection is it hits the screen, its wave function collapses as we now know its precise position. So maybe what I'll do is I'm going to get rid of one of these pages. All right. And so what you could think of is this overall picture is like the probability distribution. And you can see it's going to oscillate. We have low probability of finding an electron in the dark regions and high probability of finding it in the bright regions. So if I was to plot on top of this picture the square of the wave function as a function of, no, that's not coming up very clearly, is it? Maybe I can find a color that's going to have some more contrast. So here's phi squared as a function of position, and wherever it's dark, we have low probability of finding an electron, and wherever it's bright, we have high probability. And so it's something like this is what that wave function would look like, the square of it. And then if I was to draw the wave function for a single electron after it's hit the screen, then it would just be a sharp spike right at that position. So that's the collapse of the wave function. Okay. So we see the, let's say, familiar two-slit interference pattern after collecting thousands of electrons at the screen. All right, good. So that's sort of a recap of a lot of what we talked about last time. Are there any questions before I'm going to do like a little recap of Heisenberg uncertainty principle? All right, good. So let's do a little review of some basic aspects of the Heisenberg uncertainty principle. So I want to continue to think about de Broglie wavelengths and matter waves. This is the simplest way to do it. So let's return to de Broglie matter waves. And let's consider the following wave function. So phi versus x. Okay, so the first one that I want to think about is going to look something like this. In fact, probably move my axis over to the middle here. All right, so I'm going to draw something that looks more or less like a sinusoid. It won't be a perfect sinusoid. Maybe at the ends it deviates from a pure oscillation, but it could look something like this. Okay, so this is a possible form for some wave function. And so I could ask the question, what is the position of this particle, whatever particle has a matter wave that corresponds to this wave function? So what is the particle's position? Well, in quantum mechanics, we can't really say exactly where we're going to find a particle. All we can do is square away. Sorry, I didn't want to get rid of the square here. I'm getting ahead of myself. This is just a wave function. The square of the wave function gives a probability distribution, and it would always have to be positive. So this couldn't possibly be the square of the wave function. It's just the wave function. But what I want to do is I want to draw the square of the wave function. So what we could do is we could square phi to find the probability distribution. Okay, so let's try that. So this time I'll put my axis near the bottom. So now I'm going to square the wave function. It's going to have to be positive. Let's see, I could find, let's bring down the zeros. If I square 0, I'm still going to get 0. So those would have to line up. Something like this. And then the wave function I drew looks like a sine or a cosine, something like that. And when you square a sine or a cosine, there's a trig identity that says what happens is something like cos squared x becomes 1 plus cos of 2x all divided by 2, something like that. So the 2x, it doubles the frequency. So it's going to oscillate twice as fast, and it's going to be a function that's always positive. And so I won't be able to draw it perfectly, but it'll look something like this for the square of the wave function. Let me try again. So it has to have the same zeros, and it has to, oh God, I can't do that. Let's see if I can get this out right. And so it has to oscillate twice as quickly. Okay, and so it'll have to come back up again. All right, so it's going to be something like this. And so I can't tell you where the particle is going to be. I could tell you where it's not going to be. It's not going to be here or here or here or here or here or here. There's a bunch of zeros in the square of the wave function, so the particle is definitely not going to be there. But if I do a measurement, I have equal chance of finding it here or here or here or here or here. And so all I can do is tell you where we're likely to find the particle, not where it actually is. So we can only say where particle is likely to be found. In fact, what we can say is that for this wave function that spreads out over a large range of x values, our particle is not really localized. It's sort of extended through space. So for this wave function, the particle position is extended broadly across a wide range of x values. Okay, so that's fine, but I could ask a different question. What if I said, well, okay, I understand that you can't really identify where the particle is, but what if I asked, what is the momentum of this particle? So let's say this is question 1. And so question 2 is, what is the particle's momentum? So how do we find momentum? If I had like a matter wave, how would I figure out the momentum of some particle? What's the relationship between momentum and some kind of wave property? E is equal to what? Somebody's got to tell me.
Wavelength
What's that?
with h over wavelength.
Yeah, that's right, exactly. So it's h over lambda or h bar k, where k is 2 pi over lambda and h bar is h over 2 pi. That's exactly what it is. So well, what we could do is we could go back to our original picture of our wave function, and the wavelength is just given by the distance over which the function repeats itself. This function is not truly periodic over all space, but it's pretty periodic across here, and I can identify a pretty precise wavelength. And so we could say, well, if I take the distance between 2 zero crossings where we cross, say, with negative slope in both cases, then I could say, well, that is my lambda. And I can figure that out pretty accurately from this wave function. And so in this case, I have a lot of, if you like, uncertainty in the particle's position, but I know its momentum quite well. Okay, so we can identify lambda quite accurately from the given wave function. And therefore, we know P equals h over lambda quite precisely. And so in this first case, what we can say, this first case, we can say position is not known well. So what we might say is, let's say our uncertainty in position is large. And momentum is known well. And so we could say we have sigma p is small. Okay, so let's do a second case. second case here, if you're still writing down some of that. All right, so the second case, I'm going to draw another wave function. I think I used red, so here's x and here's y. Oh, let me put my x-axis more in the middle. All right, so this time I'm going to draw my wave function something like this. Okay, so it's like a little blip at some certain position. And so, well, what could I do if I want to find its position? Like, it's fairly obvious that this time the particle is pretty localized in some small region of space. So if I was to draw the square of this wave function, so x, here's phi squared, that's going to look something like, okay, let me drop down a couple of zeros here. So the square of the wave function is going to look something like this, the way I've drawn it. And so what we can say is, well, this time there is a pretty localized region of space where the probability is large for finding our particle, but then outside that region, the probability is either really small or kind of vanishingly small, approaching zero. So this time, what we could say is, this time, the position is rather localized. We don't know exactly where the particle will be when we do a measurement, but we can say with some pretty good confidence that it's going to fall between these dashed lines most likely, or maybe just outside those dashed lines. Therefore, sigma x in this case is small. However, now it's not so easy to identify lambda, right? If I go look at my wave function, I mean, if I want to, I can see some sort of oscillatory behavior. It goes negative just before peaking up, but I can't say with any confidence what lambda is. There is no real periodic repeating region. So not so easy to identify, and we would say sigma p is large. And so this general behavior where the more extended a wave function is, the less we know about its position and the more we know about its momentum, or vice versa. The more localized the wave function is, the more we know about its position and the less we know about its momentum. So that's a very common feature of physics in lots of different disciplines, and this is all related to Fourier analysis. Okay, so it is generally true, it is generally the case that as we know more about, say, a particle's position, or let's say in brackets momentum, the less we know about its momentum bracket position. So I could draw kind of an intermediate case. So in the intermediate case, what we would have is something like the following. So maybe there'll be a couple of oscillations, something like this. And so now what would happen is, well, the wave function is extended out further into space, so I know less about its position compared to case number 2. But it's not so delocalized that I can't say anything about its position. It's within this region, most likely. But now with a couple of little wiggles here, I start to see more of the oscillatory behavior, and I can identify a better estimate of the wavelength lambda. And so I start to know a little more about its momentum. And so it's always a trade-off. As you hone in on one variable, you lose information about the other. Okay, good. So we'll just make a couple remarks about this and then move on to the next section. So in quantum mechanics, there are pairs of variables that no matter how precisely we measure, we can never know we could never know, let's say, both with arbitrary precision. Okay, so this is expressed via the Heisenberg uncertainty principle, which says the product of your uncertainty in position and momentum has to be greater than or equal to some constant, which is h bar over 2. And you can check the units. The units make sense. Momentum is kilograms meters per second. Position is in meters. And so the combination has units of kilograms, meters squared per second. And that's a joule second. That's equivalent to a joule second, which is the units of h bar. Okay, so we will return to the Heisenberg uncertainty principle in chapter 3. All right. So now what I want to do is I want to shift gears a little bit. And we're going to do a little bit of a review of probability. And the reason that we're doing a probability review is because we're going to calculate all sorts of things from probability distributions, the probability distributions that we construct from the wave functions that we get by solving the Schrodinger equation. Okay, if you did physics 232 last year or some other time, then what we did for probability analysis in 232 is more than what we're going to do here in 304. So this should hopefully be familiar to a lot of you. So this is section 1.3, and we're going to do some probability review. All right. So review of Phys 232 material. All right, so in quantum mechanics, this quantity where we take the wave function and multiply it by its complex conjugate and construct the square of this wave function, and we're going to interpret this as a probability density. So therefore, we need to be able to calculate what are called expectation values or expected values based on a given probability density. So for us, our probability densities will come from solving Schrodinger's equation. But for what we're about to discuss, it doesn't matter. Somebody has given us a probability distribution and we need to calculate things using it. So that's the goal. So let's do this through an example. Suppose you count the number of electrons emitted from a sample in a time delta t due to beta decay or whatever. Doesn't matter. But we have some radioactive sample. Electrons are coming off the sample. We're going to count how many electrons we detect in a time interval. And then we're going to do that over and over and over again. And we'll construct a histogram of those counts. Okay, so we repeat this measurement many times. Okay, so that's the idea is pretty simple. So let's just make up some data. So this will be trial, and this will be the number of counts. So remember, we're sitting there with some kind of electron detector pointed at our radioactive sample. We have a stopwatch. We let the stopwatch go for X number of seconds, and we count N number of electrons, and we do it over and over and over again. So in the first trial, we get 13 counts, then we get 12, then we get 8, 15. It doesn't really matter. I'm just going to make up some numbers. Okay, and then this just keeps going until we do, say, capital N trials, and Cn is the number of counts we get in the nth trial. And so our trials are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to N. All right. So what we could do with these data is we could plot them as a histogram. So we're going to make an axis that's horizontal, and this is going to be the number of counts. And maybe we're going to make some bins, and we'll say, look, every time we get between 0 and 4 counts, they go in the first bin. 5, 6, 7, 8 go in the second bin. 9, 10, 11, 12 go into the third bin, and so on. And so we just do that, and we construct these bins. And if we did this experiment, we might see some results that look something like this. Maybe there's some fluctuations or something like that. Okay. And so what we're plotting on the vertical axis is the number of occurrences for a certain bin. All right. So that's fine. So we could ask some questions. Question 1. What is the mean or the average number of counts we get in a trial? Well, that's pretty easy to calculate. You just say, well, I've done N trials, maybe N is 1,000 or something like that. And all I'm going to do is I'm going to add up all of the results for the individual trials, and then just divide by N. Okay, so that's no problem. But what I want to do is I want to do the same calculation, but I'm going to manipulate this a little bit so that we can express it in a more convenient form. And what we're going to do in order to do that is we're going to notice that sometimes the outcome of a trial repeats. So I've got a 13 here, and I've got a 13 here, and I've got a 12, and a 12, and a 12. I don't think I have any others that repeats, but you could imagine that in a list of 1,000 trials, when the outcomes tend to be around 10, there's going to be lots of trials that repeat. Like I can't get 7.8 counts in a given trial. I'm going to get 7 or 8, and I'm going to get those many times if I do enough trials. So the first thing we can do is notice that some outcomes repeat. This allows us to rewrite the mean in a more useful form. Okay, so what we're going to do is we're going to say, well, if I was to sum over all counts, so this is just the sum that's in our regular expression for the mean, I could say, well, this sum has to go over sum over all measurement results, or equivalently, we sum over all trials. But that's the same thing as doing the following sum. So where I have to now be careful. So I'm gonna claim that these two are equivalent when I tell you what MJ stands for. MJ is going to be the number of times a particular outcome repeats. And we're not going to sum over the all individual trials. We're going to sum over the possible outcomes of an experiment. So for us, the possible outcomes are I saw 0 electrons in the time interval delta t, or I saw 1 or 2 or 3 or 4. So that's what this is going to sum over, the possible outcomes of an experiment, where these are the actual results of all of our trials. So now we're going to sum over the possible outcomes of an experiment. And so this is, for us, it's going to be like C could be equal to 0 or 1 or 2 and so on. And what MJ is, it's the number of times an outcome repeated in our N trials. Okay, good. So let's just be explicit where CJ specifies the possible outcome of a measurement, and MJ tells us how many times a particular outcome occurred. Looks like we have a party outside our room. Okay, so what I'm going to do is I'm going to go back to this original expression for the mean, and I'm going to replace this sum with our equivalent sum. Okay, so that's the plan. And so we say, therefore, I could write the average of C, which is just our mean, is going to be, we had a 1 over n, and so now our sum is going to be over J, and it's going to be MJ, CJ. Okay, sorry guys, we're trying to have a class here. Okay, so what I'm going to do is I'm going to move this n inside the sum. N is just a constant, so it could come inside. And so let's do this. So j equals 1 to n of mj over n cj. All right. So if a particular outcome happened mj times out of n trials, and we took a huge number of trials, what does this ratio represent? Like if I roll a die 600 times, how many times am I going to get 5? Yeah.
Oh, just for what it is, it's
Yeah.
the probability of
Yeah.
getting a result.
That's right. So if I roll a die 600 times, I'm expecting that I'll get the number 5 about 100 times. It might not be exactly 100 times, but I'll get 98 or 105 or whatever. And so I take that ratio, and it's an estimate of the probability of getting that outcome. And as I make n larger and larger and larger, this becomes a better and better estimate of that probability. Okay. So it looks like those guys don't care about me at all. That's fine. So in the limit of a large number of trials, mj over n equals pj is the probability of getting outcome j in any trial. Okay. So when we make that identification, this is pj. This is the probability of getting this cj result. All right, well, then the average of C is going to be J equals 1 to N CJ PJ. All right. Okay. So this is one of the results that we wanted. This works for a discrete probability where the outcomes are going to be some integer number, like a 1 or a 2 or a 3 or so on. And so what we're going to do is we're going to generalize this for continuous distributions. But let's just... So, sorry, we're just trying to have a class. We can hear everything I'm saying. Thank you. All right, good. So this is the sum over possible outcomes. And this is the average number of counts. And this is called the expectation value. All right. So this expectation value is not necessarily a good term because it gives the impression that what we're calculating is the result that we would expect from an experiment, but that's not what it is. Okay, so the term is a bit of a misnomer. So what I'm going to do is I'm going to draw this distribution for the beta decay again. And so this was the number of occurrences. And let's just take a look at this. If we go all the way back to here, what this sort of looks like is an exponential decay. And if you actually do the experiment, that's what you're going to find. In fact, we do a counting experiment in the 3rd year lab. So if you do the muon lifetime experiment when you take the 3rd-year lab, this is the kind of distribution that you'll see. And so in the limit of a large number of trials, it becomes a smooth distribution, and it's going to look something like this. Okay. And if I was to take a look at this distribution, here's large X, here's X equals 0. This is a probability distribution where, like, what is my most likely result of a measurement going to be? Is it going to be large X or small x? Small x. In fact, what value of X is most likely? It looks like 0, and that's exactly right. So for this exponential distribution, the most probable or most probable / likely result is X equals 0. It has the highest probability. So this is most probable. Okay, and if you were to calculate the average, well, let's just look at this. What would the average tell us? How would you locate where the average is? What's one way to do it? You have a lot of possible outcomes in the tail. So this tail extends out to infinity, but those probabilities are really low. This one has high probability, but there's few events there. So roughly, the average value is going to sit right about here. And so this is the average number of counts in a large number of trials. Okay, so what an expectation value does is it calculates the average. It doesn't calculate the most probable outcome. Okay, and so I've tried to emphasize that difference here. All right. So the next thing I want to do is say, okay, we've calculated the mean of C. So there it is, in terms of a probability. So let's imagine in our quantum mechanics picture, what we would do is we would first figure this out. And then if I wanted to calculate the average of a value, then I would just do the sum of that value times the probability over all the possible outcomes. And that's the expectation value. Okay, so if I wanted to generalize, I could do the following. So what if I wanted to calculate the average of C squared, or to be even more general, or for that matter, the average of any function of C. So f of C. So we did one of them, right? We did f of C is equal to C, the linear function. We're going to be interested in f of C is equal to C squared, but it could be anything. It could be f of C is equal to the sine of C, or e to the C to the 1/2 power, or something like that. Well, what we would do is we do exactly the same approach as before. We would say, okay, the average of f of C, we would just take all of our trials. So I equals 1 to capital N. This is, again, summing over all trials. And for each trial, we would just figure out what did we get for C. then we calculate f of c for that trial, add them all up, divide by n. That's how you calculate the average. So this is sum over all trials. But now we're going to do the exact same kind of manipulation that we did before. We could say, look, we're going to have some repeated values for C. So why don't we group all of those together? And we could say, well, I could likewise say this is 1 over n, sum of j equals 1 to little n. And so we're going to collect all of the times that we get Cj repeated, and then we're just going to multiply by that factor. Okay, so this is now not summing over trials, but summing over possible outcomes. All right. And then we do the same trick as before. We take the 1 over n inside our sum. And we say, well, this ratio is the probability of getting Cj in the limit that we did a lot of trials. And so therefore, we get our final result that the expectation value or the average of some function of C is going to be sum over all possible outcomes f of Cj times p of j. And so this is the generalization of the regular mean of C. So this is, let's say, let's call this equation A, and this is B, which is just a generalization of A. So B is a generalization of A. Okay. Good. So this is so far all written in terms of sums, and sometimes we may use this form, but in general, what we'll find is that when we do an experiment, we usually don't always have like this discrete set of possibilities, like rolling a die or drawing a card or something like that. If I was to measure the position of some particle, an electron or something like that, then maybe the electron is confined to be within some region, but between those two boundaries, it could have any position at all. So it's like a continuous function. So how do we write this down for a continuous function? You could probably guess that the sum is going to become an integral. Okay, so let's work through those details. So in the limit of a large number of trials, this probability of getting a particular outcome becomes a continuous probability density. And that's in fact the kind of thing that we can calculate from a wave function, or the square of a wave function. Okay, and so let's draw a continuous probability distribution. I'm going to draw the exponential one because that's the kind of example that we've had in mind. All right. So my first question for you is, what is the probability of getting a result X exactly, right? I have some continuous range of possible outcomes. What's the probability of getting exactly X? Yeah, 0. 0, right? If I was to say, I've got a clock and I look at the clock and I say, what's the probability that when I look at the clock, it's exactly, it's almost 3:01 and 1.2 6, 7, 8, 9, 2, 4, and I list off a million digits for the seconds. Well, the probability of getting exactly that time when I look at the clock is 0. It's vanishingly small. So all we can do is talk about what is the probability of finding x within some interval. And we can shrink that interval to be as small as we like, but we can never say exactly 0. Okay, and so what I can do is make a finite interval, and I'll make the width of that interval delta x. Okay, and so we could say the probability of measuring xj between x and x plus dx is pj is p of xj delta x. Okay, remember, oops, probability density has an area 1 underneath the curve. Okay, oh, there it is, good. So when I draw this little shaded, like almost something that's approximating a rectangle, it has some area. And whatever that shaded area is, tells us the probability of finding x at this position. If I shaded the entire area under here, I would get 1. Okay, and so what we're going to do is we're going to substitute this in to our expressions for the discrete probability expectation values. Okay, so then what we have is, if I wanted to calculate the expectation value for some function of x, what we said from the analysis that we just completed is we do the sum over all possible outcomes, f of xj times pj. Okay, this time our sum would be, I'd have to draw a whole bunch of rectangles, all of width delta x, until I filled the entire area under the curve. For this exponential distribution, that would require an infinite number of rectangles, but I could do that. All right, but we've just argued that this discrete probability can be expressed as our probability density times some width. And so really what we're doing is we're approximating this shaded area as a rectangle. We're saying that rectangle has height p of xj and it has a width of delta x. And you could see that that's an approximation because it's clearly not a rectangle, right? At the top, it's not flat, there's some curved line. But as I shrink delta x smaller and smaller and smaller, my rectangle approximation gets better and better and better. And in the limit that delta x goes to 0, this becomes an exact expression. So therefore, in the limit that delta x goes to 0, we would have the expectation value of some function of x would be the integral of f of x, p of x, dx. And in general, this would go from minus infinity to plus infinity over all possible values of x. Now, sometimes you might find that your domain for x is restricted. For example, in this probability distribution, we can't have negative x, like if x is the number of counts of a beta decay or something, you can't count negative counts. And so there you would have to adjust your limit of integration. Okay, and so this is our expectation value for a continuous probability density. And those are the types of probability densities that we get from solving Schrodinger's equation. So this is the expectation value for f of x from a continuous probability distribution. Okay. Good. All right, so we got about 10 minutes left. So let's do one other thing. I think we can finish off this probability review, and then next time we'll complete chapter 1 by talking about operators. So I don't know, in physics 200, did you talk about operators? Did you talk about momentum operators being like minus IH bar d by dx?
No, it was
So-
it was in our textbook, but
Okay.
he kind of always just wrote them down.
All right, good. So then that will be sort of our first new material, which will start, I guess, on Wednesday. Okay, so then just to wrap up this probability discussion. So in particular, for continuous distributions, we'll sometimes be interested in like the expectation value for the position of a particle. Well, in that case, our f of x is just x. And so we could say, well, that's going to be x times p of x dx. As it turns out, we will sometimes be interested in the average of the square of x for reasons that we'll see, I hope, in just a second. Well, in that case, f of x is just equal to x squared. And so it would be x squared times p of x dx. If I wanted, for some reason, to know the expectation value of the sine of x, I would just put sine of x here, or whatever function you happen to be interested in. All right. These two are useful for estimating standard deviations, and so let me show you why. So let's consider the standard deviation or the spread of a distribution. Okay, so you're probably most familiar with standard deviations from a Gaussian distribution. So here's a Gaussian distribution. Its average would sit right at the center of this symmetric distribution. So that's the expectation value of x. And then the spread is, this is plus or minus sigma. Be something like this. So I want to come up with like a general procedure for finding the spread of any distribution, not just the Gaussian distribution. Okay, so the way sigma is defined is you take 1 over n. I'm going to do the square of the standard deviation. How do you calculate standard deviation? Who knows?
Average of x squared times the square of the average of x.
Yeah, okay, so that's
Okay.
right. So you're talking about the version that we're going to get to. But yeah, you're on to something. In general, the way you do it is, this is again sum over all the number of trials. So this is sum over all trials. So what we're going to do is we're going to take the difference between the result of our individual measurement, subtract it from the average, and square it. And then we're going to add all those up and then divide by n. So that's the definition of standard deviation, or the square of the standard deviation. What I'm going to do is I'm going to do the trick that we've been doing multiple times now. I'm going to say, let's get rid of summing over all trials, and we'll sum over all possible outcomes and then account for repeated outcomes. So this will be j equals 1 to little n of mj. And then everything else stays the same. xj minus the mean squared. Okay. Now I'll bring in the 1 over n. M over n is going to be the probability. And so we're going to have sum of j equals 1 to n of xj minus the mean squared. And then we have pj. This is for a discrete distribution. And you could imagine, I won't do it, but if we wanted to talk about a continuous distribution, this pj we would replace with p of x times delta x, and then we would take the limit that delta x goes to 0. Or sigma squared is equal to the integral of x minus x average squared p of x dx for a continuous distribution. Okay, so this is one form for finding the square of the standard deviation. But what I'd like to do is do a little manipulation to get at what you were proposing. And I think we can do that in the 4 minutes that we have left. Okay, so to get another form for sigma squared, let's expand the square. Okay, so sigma squared is equal to the integral. And so now I want to expand the square. So we're going to get x squared minus, there's a cross term, 2x average times x. And then we're going to get plus x average squared. And then we still have p of x dx. All right. So what I'm going to do is I'm just going to consider these terms one by one. So we have the integral of a sum of terms. We could write that as a sum of integrals. So the first one, there's not much we can do. X squared p of x dx. Not much we can do with that one. But then we have this second term here. 2 is obviously a constant. It's going to be pulled outside. But this x bar, or sorry, x average, the expectation value, is just some number. It's also a constant. It comes outside the integral. So we have minus 2 x average. And then we have the integral of x, e of x dx. And then I'm going to have plus. This is also just a constant. It's the average squared. So it's just some number. So it comes outside. And then we have x squared averaged integral of p of x dx. All right. So let's start with the easy one. What's this? I integrate the probability over all possible values of x. Well, 1. I'm calculating, yeah, it's the area under my probability distribution. And if that's normalized, that area should be 1. All right. What's this x p of x integrated over x? X p of x integrated over x. That's just the average of x. And while we're here, x squared p of x dx is the average of x squared. So this is going to be the average of x. And this one is going to be the average of x squared. All right. So if we bring all of that together, we say therefore, what are we calculating? Sigma squared. And so we'll just write out all our terms. The first term is the average of x squared. And then we have 2 minus 2, the average of x times the average of x. So that's the average of x all squared. And then we have plus the average of x squared times 1. Sorry, that's wrong. The average of x squared times 1. All right. But these two last terms are both like have x squared in them. And so it's minus 2 plus 1. And so all of this combines just to be a minus x average squared. And so this is what you were getting at. This square of the standard deviation could be written as x squared averaged minus x averaged and then squared. And so these two expressions, let's go Roman numeral, lowercase Roman numeral I and I2 are equivalent. So equations I and double I are equivalent. Okay, good. So I think that's where I'm going to stop for today. What we're going to start next time is in your textbook, if you want to orient yourselves, is we're starting section 1.5 next time. That's going to be new material. And what we'll do is we'll start talking about operators. What I might do is maybe I'll come up with an example to just preview or review some of this probability stuff. And then we'll get into operators in quantum mechanics and we'll start digging into new material. All right. Thank you very much, everyone. Have a good couple days and we'll see you on Wednesday.